Hello and welcome back to Special Relativity. What we're going to do today is to investigate 6 separate properties of the Lorentz Transformations. We'll talk about the distinction between so-called world pictures and world maps, length contraction, time dilation, and if time, the twin paradox. But just as a quick piece of revision regarding the Lorentz Transformations, remember that we had 2 inertial reference frames in standard configuration with respect to one another. The latter, which is called S prime, the latter inertial frame is moving relative to S with a velocity v in the positive x direction. We have x and x prime, y and y prime, z and z prime, and t prime. And the click, the most basic event, or the most basic object, sorry, an event P, a click, a point in space-time. This event will have descriptor, space-time coordinates x, y, z, t, according to S. But according to S prime, those space-time coordinates are the same event. And again, I emphasize this click is a geometric object that exists independently of how we choose to coordinatize space-time. That event, P, has this descriptor in S and this descriptor in an inertial frame S prime. And the Lorentz Transformations, equations 56, showed us how to convert x, y, z, t into x prime, y prime, z prime, t prime. And this was a set of linear equations. These transformations are linear. Hence the strong correspondence between linear algebra and relativity. We have a so-called gamma factor, a Lorentz gamma factor, as follows. And then our transformation formulae for y and z are unchanged from the Galilean versions, but the time and the x coordinate are transformed differently. And they transform as follows. So these are the Lorentz Transformations, which we derived in the last class, and some consequences of which we want to study in section 10. So the first thing we want to study, the first of 6 consequences in this section, is the idea of the relativity of simultaneity. Now, we covered this briefly at the end of the last class, but I'm going to quickly revise it again. We're going to have 2 events which happen like this. Yep. So according to S, we're going to have 2 events which happen at x1, t and x2, t respectively. So this is a pair of clicks which happen simultaneously according to frame S. And this is the x-axis of frame S. And the question is, what happens when you transform these, when you Lorentz transform to frame S prime? And always we have standard configuration. Well, x1 is going to become x1 prime. T is going to become I actually want to put a subscript on this t1 prime because they're going to be different in general. x2 is going to become x2 prime, but t is going to become t2 prime. If time were absolute, then these things would be equal, but they're not. When you transform this pair of events using the Lorentz transformations and you calculate t2 prime minus t1 prime, what you get is not 0. Instead, you get the following. And by the way, if c were formally taken to infinity, or if v is much, much less than c, this thing here is going to vanish. So time is absolute if you take c to be infinite, or arbitrarily large compared to v. But otherwise, these 2 events, which were simultaneous in one frame, are not simultaneous in the other. So t1 prime doesn't equal t2 prime. So this is a direct consequence of the Lorentz transformations, and in particular, the plasticity of time, which is expressed in the first equation. Again, as I said twice before, we have very finely developed intuition for the non-infinite nature of the speed of sound. We have terrible intuition for the non-infinite nature of the speed of light. In fact, much of our intuition implicitly assumes the speed of light is infinite, and the idea of an absolute time the idea of an absolute time is actually inconsistent with the non-infinite C. Now this is a direct consequence of the linear equations given here, but the derivation's a bit unsatisfactory because I say, all right, you throw in the Lorentz transformation equations, this pops out, and this does not equal naught if you have two spatially distinct points. But it's unsatisfying perhaps from a conceptual perspective, so I want to give a second demonstration of the concept of time being, the concept of simultaneity being relative. In other words, two events that are simultaneous with respect to one observer are not necessarily going to be simultaneous with respect to another. And so this second demonstration is called Einstein's Train. And this just makes the point that the non-infinite speed of light is consistent with time differences or simultaneity being relative rather than absolute. So we're going to have frame S associated with an observer standing at some point M on an embankment. And this observer M has a ruler, and they know that they're at the midpoint between points A and B. Because they got their ruler, they measured distances. The ruler was always stationary relative to the embankment, and they're at exactly the midpoint between points A and B. Try and draw it a bit more to scale. They're exactly at the midpoint between points A and B on this embankment. And they, there's a thunderstorm, and and lightning strikes at point A and B simultaneously according to them. How do they know that the event lightning struck A and the event lightning struck B are simultaneous? Well, they know because they know that they're standing at the midpoint between A and B, because they measured it, and the light from A strikes their eye. Let's imagine that this is a one-dimensional being of zero size. They detect the light from A and the light from B at this point here simultaneously. Remember that when you look at me, you see me over here, but actually everything's happening locally in your head. You're collecting light waves, you're collecting sound waves. Sort of everything that you see is about measurements that you detect locally with your senses. Similarly here, the way that M knows that lightning struck A is because the light travels and bangs into their eye. Similarly from B, M knows that the event lightning struck A and the event lightning struck B are simultaneous because the light reaches them from A and B at the same time. Now, Einstein was not an artist. This is Einstein's depiction of a train. But if you're Einstein, you can do whatever the hell you want. So we're going to have Einstein's train here, which is moving at some speed v in the positive x/x prime direction. So this train is now s prime. The embankment is s. So the train is s. And we're going to have an observer, m prime. Again, this is an idealized thing. These observers are infinitely small points. They're infinitely close together so that they can be considered coincident. And at a given instant of time, which according to S is when they receive the light signals, these two observers are infinitely close together, so idealized. But here's the point. The concept of simultaneity being relative is directly connected with the idea that light does not travel at an infinite speed, because according to M, lightning will strike A and B simultaneously. Why? Because they waited and those two light pulses banged into M at some later time simultaneously. But it's very clear from this diagram here that when, according to S, lightning strikes A and B simultaneously and the light's going this way, but this point M is moving to the right. And the point is that M prime, the moving observer, moving relative to S, the idea of motion has no absolute meaning, only relative motion. M prime is moving relative to M, and the light from B will strike M prime before the light from A strikes M prime because M prime is moving to the right. Hence, M prime will say that the event lightning struck B occurs before the event lightning struck A. And this is going to tell you how to calculate that time difference between those two events, which are judged simultaneous in one frame, but not from the other. But this captures the essence of it, the fact that the speed of light is not infinite. Again, when you first see these arguments, they seem, they're certainly counterintuitive, that's part of the point. They're using the light of logic to deduce these shocking consequences of the Lorentz transformations. But this is just a careful chain of argument which ultimately derives consequences of Einstein's two axioms. Next is the Newtonian limit of the Lorentz transformations. Now, I've said probably too many times already that, and at the risk of annoying you, new theories have to reduce to the old in the domain of validity of the latter. So you should get the Galilean transformations as a limit case of the Lorentz transformations. If we consider V on C to tend to 1, if we consider, and under this limit, the gamma factor will tend to 1. Yep. And any division by C is going to disappear. So these things, well, the gammas are going to be 1. Anything where you divide by C will disappear. So our first equation becomes T prime equals T, which is Newton's absolute time. You know, you wouldn't even bother to write it down, right? But gamma's 1, this disappears. Second equation, gamma's 1, we get x prime equals x minus vt. Yes, thank you. So the statement is, shouldn't it be V on C goes to 0? Absolutely, V on C is going to 0. So not V on C goes to 1, but rather V on C goes to 0. Thank you. We have this limit case, and similarly, y prime equals y and z prime equals z are unchanged. This is the higher theory reducing to, in this case, the Galilean transformations of Newtonian mechanics in the appropriate limit as V on C tends to 0 from above, tends to 0, and gamma hence tends to 1. The next thing I want to look at is the difference and differential versions. And this is 10.3. So this is the difference and differential versions of the Lorentz transformations. So the difference and differential Lorentz transformations. So let me write the Lorentz transformations once again, leaving a judicious gap. Yep. Gamma factor T minus V x on C squared, x prime, etc. Now the key point which I've already said is that, or a key point is that these things are linear transformations. So this is about one event in space-time. Yep, one event, one click, one dot, a P, right? If you're talking about coordinate differences, you're talking about two events, and those two events could happen at different points in space, at different instants of time, relative to some observer. And in the sense we're talking about when we have a difference, you're actually talking about a vector in space-time that connects two events. And the question is, how do those events transform? So you'll have a pair of events, for example, x1, y1, z1, t1, and x2, y2, z2, t2. And you want to transform the difference between these. So you could write this out with a 1 subscript on all the x, y, z's and t's, etc. You could write it out again for event 2, putting a 2 subscript on everything. Then you could subtract the equations, and you could define delta x equals x2 minus x1. Similarly for delta y, delta z, delta t. And similarly delta x prime would be x2 prime minus x1 prime, etc. But when you subtracted the two equations, as a consequence of their linearity, you'd actually get equations that have exactly the same structure, or more precisely, they're linear and homogeneous. There's no constants here. The point is that coordinate differences transform in exactly the same way as the coordinates as a consequence of the linearity of these transformations. So this is the difference form of the Lorentz transformations. And if you were to have infinitesimal differences, you wanted a differential form, you want these events to be arbitrarily close together in one inertial frame. You just write out exactly the same formulas, and you would place the capital D for a finite but small increment, or finite increment, with an infinitesimal. So dt prime would equal gamma, dt, etc. And that would be the differential forms of the Lorentz transformations. I won't write those out. So this is our fourth consequence. Our fifth, so that's our third. I'm getting ahead of myself. So our fourth consequence is to actually introduce an absolute, the Lorentz invariants. So when we speak of Lorentz invariants, we're talking about absolutes. We're talking about quantities that are unchanged under a Lorentz transformation. We already have one absolute, which is C. At the risk of being vague, another absolute is the physical world. The physical world exists as a geometric object independently of how we choose to do our physics and independently of how we choose to coordinatize space-time. So physical reality is in some sense an invariant. Now that latter point is quite a deep one and ultimately leads us to a tensorial formulation, a tensor analysis formulation of relativity, but that's a story for a later lecture. Bertrand Russell, the famous philosopher, mathematician, also pretty good physicist, once said that the name special relativity is a bit of a misnomer because ultimately what you're doing is you're getting things that are absolutes, not relative but are actually absolutes. You're actually getting at the physical world itself in a way that transcends a multiplicity of different descriptions according to different frames of reference. So here's another absolute for you with all that preamble. The Lorentz invariants, in other words, things that are unchanged under Lorentz transformations of this new object called the squared interval. It's actually a space-time version of distance squared. And that's actually a good analogy. I talk about geometric objects. This is a geometric object, and it has a certain property which is called length, right? And you could say that this is a vector relative to some origin, and you could describe the origin and the tip of this vector in any coordinate system you want. And if you change coordinate systems, for example, if you have an x, y, z, t and you change it, then certainly the numbers that describe this position and this position will change. And so the vectors themselves are position vectors which connect the origin, which is where my fingers join, to each of these ends, will change. But the length of this object doesn't change. Yep. So watch this. The length of the stick doesn't change. Now that's trivial, but it's also profound, right? The length and the length squared of this object is invariant under coordinate transformations. We want to have a space-time equivalent of this, except instead of this plastic stick connecting 2 points in space, we actually want to connect 2 points in space-time, a bit like the top left of the upper board. We want to calculate an absolute quantity, something upon which all inertial observers agree. So this is space-time. Here's going to be two events, P and Q. And the observers will not agree on how to describe these events, because S will say the events have the coordinates P and Q, x1, y1, z1, t1, x2, y2, z2, t2. S prime will say, no, it's actually P prime and Q prime. Those same events, S got it wrong, S prime rather, says that these events are x1 prime, x2 prime, etc. They'll disagree. But we want some generalization on a squared length, and we're going to call this delta S squared, the so-called squared interval. This is going to be something upon which the observers will agree, the so-called squared interval. Even though they'll disagree on x1, y1, z1, t1, etc., they will agree on this squared interval, delta S squared. We're actually going to begin with the Einstein law of light propagation. Suppose that you have a click, and when you click in S, a spherical shell of light expands from that point. So you'll have a set of points, x, y, z, t, according to S. And that set of points associated with this expanding spherical shell of light that was emitted at the origin of S's coordinate system at t equals 0. The points x, y, z, t on that expanding spherical shell of light will obey this equation. X squared plus y squared plus z squared, by Pythagoras' theorem, is the distance squared that light travels, and the distance is ct. So this set of points, x, y, z, t, that obey this equation corresponds to a light pulse expanding from the origin of space-time, expanding in the future. By the way, in the past it contracts to a point and then expands again. This thing is called the light cone. I'll talk more about light cones in the context of the causal structure of space-time soon enough. But for now, let me just give this a name, the light cone. I'll justify why it's called a cone at some later date. So let's shove the right-hand side onto the left-hand side and set this to 0. Same thing. So this is a surface in space-time associated with the expanding shell of light. Now, by Einstein's law of light propagation, if we go to S prime in the standard configuration, we just prime everything. C stays the same, however, it's an absolute, and you'll get this equation. Now, this is the same surface in space-time. You've just coordinatized that surface differently. Yep. If we had two rather than three spatial dimensions, you'd have something like this, an expanding circle of light. You can see why it's called the cone. Yep. And if we go back in the future, you have the so-called backwards light cone. But this is a surface in space-time, and you pick a point on that surface, and you coordinatize it with x, y, z, t if you're in S, or x prime, z prime, y prime, t prime according to S prime. And this is describing the same object from two different coordinate systems, but these things are equal. So what we've just learned, and so I let this be the origin of space-time, x equals y equals z equals t equals 0 according to S. But we could also have this as an event P and an event Q to give you an arbitrary pair of events. So you pick an arbitrary point in space-time, coordinatize it however you want, set out a spherical shell of light from that point, fill space-time with this surface. In fact, it's a hypersurface that fills space-time. It's a three-dimensional hypersurface embedded in four space-time dimensions. Points on that hypersurface, according to S, obey this equation. According to S prime, obey this equation, except we're going to need a differential form. And that differential form will be delta x squared plus delta y squared plus delta z squared, etc. Now, this argument reveals a new absolute. And when I say delta t squared, I mean delta t all squared, yep, and similarly elsewhere. We've discovered a new absolute, this so-called squared interval. You have two events, and you define delta s squared to be this. Now, I'm multiplying it by -1, makes no difference. Half the relativity books will multiply by -1 and half won't. There's no consistency. But the point is that this is a quantity upon which all inertial observers will agree. So if you're in frame S, you'd have a particular delta t, particular delta x, etc. Associated with a pair of events, P and Q, whether or not they can be connected with a light cone. So we're actually pulling Q off the light cone now. I haven't justified that. Have a think about it. S prime would say, no, it's not delta t, it's delta t prime, and it's not delta x, it's delta x prime, etc. So different inertial observers would certainly disagree on the coordinates of the difference vector, delta x, delta y, delta z, delta t, or delta x prime, delta y prime, etc. But they would all agree on the value of this quantity here. So this is an absolute. This is a Lorentz invariant. This is a quantity upon which all inertial observers agree. It must therefore have a geometric significance that transcends any particular coordinatization of space-time. This is to space-time what length or length squared is to Euclidean space. However, this space is not Euclidean, right? So Pythagoras' theorem does not work in this space. We'll get to this point a little later in more depth. This is not a Euclidean space, and so it has properties that are utterly unlike Euclidean space. Yeah? Absolutely. So this is just zero for a pair of events that can be connected by a light signal. But this right-hand side in general won't be zero for pairs of points that, or events more precisely, that can't be connected with a light signal. So for events or coordinate differences in space-time that can be connected by a light signal in vacuum, absolutely this will be zero. But I'm considering the more general case where you don't have both points on a light cone. If you have a light cone emitted from the first event, the second event Q does not necessarily pass through the light cone, so this is not necessarily zero. So we have this new absolute, and you can show explicitly that this thing is invariant under Lorentz transformations for any pair of points in space-time, and this is left as an exercise 15. By the way, you can also use you can demand the Lorentz invariance of the squared interval as a way of actually deriving the Lorentz transformations. I won't go through that. We've already met the idea of C as a speed limit, as a relativistic speed limit, as an empirical observation from nature. What I want to do here is to set up a link between C as a speed limit and causality. Yep. So the idea of C as a speed limit and causality are deeply connected. What do I mean by causality? I mean the following. I don't give a stuff how plastic time is according to the Lorentz transformations. I don't give a stuff about relativity of simultaneity. You can have that. But if a cause precedes an effect in one inertial frame, if we can call P a cause, it's an event that led to some effect, Q. I don't care how plastic space-time is. If P occurred before Q in one inertial frame, and this is a cause and effect, right? I can't click my fingers and then 1 microsecond later on Alpha Centauri have an effect due to my click, right? I'm talking about signals travelling at less than or equal to the speed of light. We're going to demand that if a cause precedes an effect, in one inertial frame it must precede the effect in all inertial frames. To be more precise, we're going to take this demand for causality, and I'll make this precise soon, that if a cause precedes an effect in one frame, inertial frame, it must precede the effect in all inertial frames. I'm going to mix this with the assumed truth of the Lorentz transformations, and together get C as a speed limit. If, by the way, you're quite happy for causality to be screwed around, if you don't want cause precedes an effect in one frame, if you are happy for the effect to happen before the cause in another frame, this argument won't hold, and you can have tachyons if you want. But as often happens in science fiction shows, such as Red Dwarf, which I was watching yesterday, if you allow for superluminal motion, then the order of cause and effect can be reversed. And we say, look, I know physics screws with your mind and has all these weird effects, but I don't want causality to be touched. So we're going to show how causality plus the Lorentz transformations implies that C is a speed limit. And this is nice. We're going to do a proof by contradiction. So for those of you who have not seen a proof by contradiction before, it's the following. And it's a bit of a torturous chain of logic. You assume that what you want to prove is false. You show that as a logical consequence of that assumption, that what you want to prove is false, that this leads to an absurdity. Hence your initial assumption that what you wanted to prove is false is itself false. Hence what you wanted to prove is true. So pretty torturous chain of logic, and I'll repeat it. Assume the falsity of what you want to prove, derive a logical contradiction thereof, hence the initial assumption that what you wanted to prove is false is itself false, hence what you wanted to assume is true. Now that's compact statement of proof by contradiction. When I first heard it, I didn't like it. I said, what a stupid way to prove things. Please spend 10 minutes on the internet looking up proof by contradiction, and then ask yourself, do you believe this is a way of proving things? But I want to use proof by contradiction. And so what I'm going to do is assume that C is not a speed limit. Assume that a cause can lead to an effect at superluminal speeds. So I can click my fingers, and a microsecond later something happens on Alpha Centauri, despite the fact that light couldn't get there in time. Assume that superluminal causal influence exists. Sorry, start again. I need to look at my notes. We're going to assume... I've lost the plot. That's not good. It made sense on the train this morning. So we're going to assume that superluminal signals exist, and we're going to show that this violates causality. So we're going to assume that superluminal signals exist. This is going to violate causality, which is going to be the logical contradiction, because we want to assume as a hypothesis the truth of causality. But let's do it, and you'll see what I mean. So I'm going to have a cause and an effect. And the cause I'm going to call P according to S. And that cause is going to, let's just work in one spatial dimension. So this is x comma t. Yep, x comma t. This is going to be the cause, and this is going to be the effect. P leads to Q. And this is all going to be in frame S. The cause is the click at x equals t equals naught, and the effect is going to happen at x comma t. Those same events, the cause P and the effect Q, are going to be called P prime and Q prime, according to S prime. And how do you get P prime and Q prime? You Lorentz transform. Yep. You Lorentz transform. And you'll find that P prime is x prime equals naught, and t prime equals naught, and you'll find that Q prime is gamma into x minus vt, t minus vx on c squared. So here we have the cause and effect described in two different inertial frames. Now I want to assume the opposite of what I want to prove. Now we've demonstrated the Lorentz transformations. I want to assume that causality is not respected. I want to assume that x is greater than ct, that the event that happened at the space-time origin can have a causal influence at some point x, t in space-time, with x greater than ct. So this would be superluminal. So we could write x as ct plus delta, where delta is some real positive number, which I write as follows. Delta is a real positive number. So we're assuming the opposite of what we want to prove. We're assuming that c is not a speed limit. Now, let eta be the time difference between the two events, according to S. And the time difference between the two events, according to S, will be t, which by assumption is greater than naught. As far as S is concerned, P is the cause and Q is the effect. X doesn't equal naught, T is greater than naught. We now transform to S prime to get the time difference eta prime, which is going to be gamma into T minus Vx on C squared. Yep. So we have this eta prime, which is gamma into T minus Vx on C squared. We now make use of this thing here to replace the x with ct plus delta. Good. So what you have is that this time difference, this time difference between the events, according to S prime, is given by the following, which I could rearrange into this expression here. And it's this minus sign that's going to give us what we want. Why? Because you can choose inertial reference frames. you can choose inertial reference frames with V arbitrarily close to C. Yep. So you could let V tend towards C minus epsilon, where epsilon is real and positive. And if you choose this so-called boost velocity V to be arbitrarily close to the speed of light, but just below it, this thing is going to tend towards naught. And so this whole thing is going to converge towards negative V delta gamma on C squared, which is less than naught. So we assumed the falsity of what we wanted to prove, that C is not a speed limit. We allowed superluminal propagation, and we obtained a logical contradiction that the temporal order of a cause and an effect could be reversed upon a certain Lorentz transformation. And this is in contradiction to our cherished causality that we don't want to let go of. Hence the initial assumption that C is not a speed limit is incorrect, hence C is an absolute speed limit. Now again, if I was sitting in your shoes, I'd be a bit dissatisfied with this. I'd say, you know, you've pulled these sneaky tricks to make this profound connection between causality and C as a speed limit. I don't believe it. So I invite you to challenge this argument, to argue and debate this amongst yourselves, to ask the question, do you buy this or not? And if not, how can you modify the argument? And if you do believe it, why? Can you justify that in debate with others? But the claim here is that this is a proof of a link between causality and Lorentz transformations, the demand for causality, together with, as defined earlier, together with the Lorentz transformations imply that C is a speed limit. So that's kind of cool. I want to move on to the group properties of the Lorentz transformations, and this is a group in the mathematical sense of the term, of a mathematical group. So the group properties of the Lorentz transformations. Now, the Lorentz transformations, as I mentioned earlier, are linear coordinate transformations. If we go back to the top right of the middle board, equations 56, this is a linear transformation. Now we could write equations 56, the Lorentz transformations, as in a matrix form if we wanted to. T prime, x prime, y prime, z prime equals some 4x4 matrix, the coefficients of which are consistent with equation 56. Yep. And so we're thinking of, I keep talking about geometric objects, these points in space-time, coordinatized in one or another coordinate system, are vectors in space-time. And the Lorentz transformations are going to be some matrix. So let me put a double underline to denote this as being a matrix, the Lorentz transformation matrix. And this is actually a set of matrices coordinatized by the boost velocities v, which can lie anywhere between, but not including negative c and c. Yep. So this is a set of matrices where v is the boost velocities between minus c and c, with the endpoints excluded. So this is a set of matrices, and I want to show that this set of matrices forms a mathematical group. So a mathematical group is a set of operations, and here we have a set of operations, a set of Lorentz transformations, together with a binary operator. So I want to be general here. So instead of speaking of a set of elements L, I'm going to have a set of elements capital G. So capital G is some set of elements, or set of operations, A, B, C, etc. Now this notation suggests that this is a countable set. In fact, we have an uncountable set. That doesn't matter. It doesn't change the definitions I'm going to give. We have some set of operations, A, B, C, etc. And also the idea that you can have a binary operator that lets you form a product of such operations. So A, B, right? Now you can just have two Lorentz transformations, right? You have some space-time vector. You multiply by some Lorentz transformation matrix L of V1. You could then do a second Lorentz transformation. How do you put those two Lorentz transformations together? You know how to multiply two 4x4 matrices. So we have the idea of a binary operation that can take a pair of Lorentz transformations and produce a third Lorentz transformation. So with that preamble, we can ask the question, is the set of all Lorentz transformations a group in the mathematical sense of the term? If it is, by the way, we can call it the Lorentz group. It is a group, and you'll show that in an exercise. Here I just want to point out the axioms that a set of elements together with a certain binary operation must obey in order to qualify as a mathematical group. So there's 4 axioms I need, and I'll write these in mathematical language, but I'll explain them in English. So for all, which is the upside down A, for all, A and B within the group, the product AB must be in the group. In other words, 2 Lorentz transformations corresponds to a third valid Lorentz transformation. The second axiom that you'll need to prove is that there exists, now that's a backwards E, so there exists a unit element, which we call I for unit or 1. It's a generalization of 1. There exists a unit element in G such that, which I'll denote by a vertical line, such that for all A within G, we have the unit times A equals A times the unit equals A. And by the way, the unit is just going to be a unit 4x4 matrix. Third of 4 axioms that you need to demonstrate consistency with in order to call the set of Lorentz transforms a Lorentz group is that for all A within the group G, there exists an inverse which we'll call A to the minus 1, such that the vertical line A times its inverse equals the inverse of A times A, which equals the unit I. So inverses exist. There exists an inverse Lorentz transformation that will undo any particular Lorentz transformation. And the 4th axiom we're going to need is associativity. Yep. For all A, B, C in the group, what you want is this to hold. Matrix multiplication, by the way, is associative. So these are the 4 things, the 4 axioms you need to demonstrate that the Lorentz transformations obey in order to be able to call the set of Lorentz transformation matrices a group. And what you'll find is that in the exercise, it's a bit of a boring exercise, but it shows something very deep, that the Lorentz transformations form a mathematical group, which again is called the Lorentz group. I now want to move on to chapter 4, which is called Relativistic Kinematics. So section 11, which is called World Pictures and World Maps. So world pictures and world maps. So when you gaze at the moon, so this is you as a physicist gazing at the moon against a backdrop of stars, then you see the moon as it was, according to you, a little over a second ago, because that's how long it takes light, just over a second, to travel from the moon to you as an observer. But you'll see the stars as they were many thousands of years ago, according to your inertial frame S. The point here is that what you actually see at some instant of your time, we speak of your time because time is not absolute, what you see at some instant of your time is actually a very complicated construct of events that occurred progressively further back in your past. The event, the photon struck the moon, occurred a second before you observed that photon, reflected from the surface of the moon. The event, Alpha Centauri emitted a photon, occurred, I don't know how long it takes. How far away is Alpha Centauri? 4.3 beautiful, 4.3 light years. So the event, this gas molecule on Alpha Centauri emitted a photon, will occur 4.3 years before, according to you, the instant at which that photon is absorbed by your eye. So when you look at the world around you as an inertial observer, what you see is a world picture, what we call a world picture here, which again is a very complicated amalgam of events that occurred progressively further back in your past. It's actually quite a complicated construct, but we're going to call this a world picture. And with one exception, we're never going to look at world pictures again, right? With one important exception, which is the tram. What would a relativistic tram look like? On the other hand, we can have world maps, and this is something which is a much simpler construct. Choose a particular instant of your time. So I'm an inertial observer. I click my fingers and I ask the question. If I click my fingers, then my time t equals t0, and I want to freeze the entire world at that time. What does it look like? This is called a world map. Yeah? And for the remainder of this course, with one exception, when we look at relativistic trams, we'll be speaking always of world maps. This distinction, by the way, between world maps and world pictures is often not explicitly made. I won't often explicitly make it, but it's very, very important to bear in mind. I want to move on to section 13, which is on time dilation. Section 12, which is length contraction. So this is often summarised as moving rulers shrink. So we're going to have two inertial frames in the usual standard configuration. And we're going to attach a ruler to one of the frames. This ruler is going to be stationary relative to frame S prime. Fair enough. Now I'm going to begin with the differential form of the difference form of the Lorentz Transformations equation here. So delta x prime, equals gamma, etc. So we have two events. And those two events are going to be associated with the click that occurs at each end of this ruler. So this, as far as S is concerned, is a flying ruler. So we have a flying ruler, and S is clever. S knows that for a flying ruler, in order to measure its length, imagine the ruler's flying past you, you're going to need to click simultaneously at each end of the flying ruler. So as the ruler flies past, when one end of the ruler touches this hand, the other end touches this hand, and I click simultaneously, and I'll have two events, which is simultaneous according to S, and that's how I'm going to measure in S the flying ruler. So S is doing the measuring of what to her is a flying ruler S, and since S measures the two ends of the ruler simultaneously, delta t would be naught. Now, I've left the prime off here. I've left this prime off. Fair enough. So we get this equation. Now, I'm going to call delta x the length L ascribed to the ruler in the unprimed frame. Delta x prime, I could call that L prime the length ascribed to the ruler in S prime frame. Instead, I'm going to call it L subscript naught. This is the so-called rest length of the ruler. The length that the ruler has when it's stationary, relative to what you learn, is an L naught divided by gamma equals L. In other words, the moving ruler, moving at speed v relative to u, has a length which is different. In fact, you need to multiply the rest length by something bigger than 1 in order to get the moving length. In other words, the moving ruler has shrunk by a length, by this factor here. It's shrunk by this factor, according to S prime, according to S. Now this, again, is one of those unsatisfactory derivations for which the physics is not immediately transparent. I'm actually going to be slightly facetious and not give you a physically pleasing derivation of this phenomenon of length contraction, but I'll leave it to you to come up with such a physical explanation. If you want a hint, look at section 13 of the notes, with which I'll begin the next class. Thank you, as always.